Yeah, hey everyone. I hope our broadcast has started. So, hello everyone. Glad to see you on our third lecture on Arcane Finance, organized by Arcane Finance on Aleo. So we are building a privacy-centric DEX on Aleo, and while giving this, creating also this educational content for everyone, because we are very excited about Aleo and want more people to know about it and to build on Aleo. So our first two lectures were theoretical. So the first one covered the landscape of blockchains and where Aleo's place is, and the second one was about Leo programming language and its primitives and the third one, we decided to do it as a live coding session. So there is an instruction on how to prepare your development environment on Aleo and on Aleo's side, I mean. And I won't be going through this on this lecture. So I expect you do this on your own. So the instructions are pretty good, and I hope you won't face any difficulties. So let's go to Visual Studio. Okay, yeah, I think it worked. So now today we'll create a very simple program on Aleo. So it will be a toy automatic market maker contract. So again, it won't be real, but I will try to show you kind of the thought process on how to use it, how to use Leo for creating programs. Okay, so I will use the command Leo new toy AMM. Okay. Oops. Underscore. Okay, and okay, I will go and open the folder. Actually, can I do this? Toy code dot. So let me check that you can see. Okay. Sorry, I'm pretty new to YouTubing and streaming, and there are some some difficulties along the way. Okay, here we are. So there is a new program. So it's like hello worldish program created automatically by Leo console tool. So let's start building our AMM. So what is essentially an AMM is, just a quick refresh. So it is an exchange, decentralized exchange, where people can deposit their tokens, and they will be able to swap one token into another token. And this is the price at which the tokens are exchanged are defined by the amount of tokens in the pool. So people provide liquidity, deposit their tokens, and then swaps happen, and the price is changed according to market, to what token people want more. Okay. So yeah, let's think like what will we need to do that. We will need several things. So we'll start from the very basic thing, which is tokens. Okay, so we will again, this is a toy example, not real one, so I will define just two tokens. So these are records. Records records have fields, and these fields have types. So token 1 has a field owner and field amount. So each record represents a certain amount of tokens belonging to a certain owner. And the I think, yeah, shouldn't be semicolon, it should be a comma, and yeah. So I'm defining just two tokens that are hard-coded in the program. I mean, in a real AMM, we would define a more abstract token structure that has a symbol, a name, a decimal point, decimal amount, and stuff like that. So this would be more similar to like traditional ERC20 contract. Okay. So we define tokens. Yeah, so currently our program cannot do anything, and well, let's start with minting these tokens. Mint token 1, and the other transition will be mint token 2. Okay, so, well, there will be a couple of arguments. So address of the owner who's minting the token, and the amount to be minted. So as well, this program will be deployed on testnet. So there is so basically anyone can come and mint as many tokens as they want. So real world example would be, I mean, real world program would be slightly different, of course. Yeah. Okay, and token 2 will do pretty similar. Okay, so we're minting. Yeah, so I think it's worth noting that everything that we all the code that we wrote so far deals with private things. So the fields of the records are private by default, and also arguments of transitions are private by default. So everything is private, and yeah, cannot be seen by someone who is just watching what's going on in Explorer, in Aleo Explorer. Okay. Well, as we have tokens, probably we'll want to transfer them too. So let's create a transition to transfer tokens. So let it be like a receiver and amount. And the result will be 2 tokens. So the one will represent what receiver will receive, and the other will represent the change. Okay. So okay, like send token is a token that so I'm creating the record. I'm defining the variable send token of type token 1, and well, token 1 is owner is receiver, and the amount is amount. Okay, and the other token will be change token. It's also of type token1, and what it allows, how it works. So the owner will be the owner of, oh, okay, I see. I forgot to pass the source of this transfer, so what is being transferred. Okay, so owner is token owner, and amount is the amount of original token minus the amount that was sent to the receiver. And yeah, essentially this this operation, so when we do minus, is checking automatically that the token amount is more than this amount. So it's unlike default behavior of older Solidity versions, the amount. So there is no automatic wrapping. So you cannot like overflow or underflow. So the exception will be thrown in this case. Okay, and I will return both of these tokens, tuple of these tokens. Okay, yep, something's wrong. Yeah. So we transferred token number 1. Well, I think I'll skip probably writing the same code for token 2, as yeah, it will take probably too much time to do this for both tokens. Okay, so let's move further and like closer to swapping and yeah, liquidity management and stuff like that. So far, as you can see, our program doesn't have any storage, so there are no mappings, so there is no state. The program has no state, and we are going to change this. So what we need to store, let's think. So people will be depositing some liquidity into our AMM pool. Well, we have a single pool for token number 1 and token number 2, and well, we'll need to store somewhere what are our reserves for each of the tokens. So let's define reserves that maps token token index to the amount. Well, essentially it means token 1 reserves and 2 token 2 reserves. Yeah, we have to use mappings, as currently Aleo do not allow to define top level variables like fields of the program. So I cannot write something like reserve token 1 and reserve token 2. So I probably would do this if it was allowed, but it is not allowed, and we have to use mappings for everything. Okay, so reserves, and what else we need? We need total supply of the LP token supply, essentially. That will be calculated. Yeah, LP total supply. LP stands for liquidity provided by users. Okay, and also we'll have LP balances that will represent the deposits of the users. So we'll have to understand, like, if you added liquidity to an AMM, you'll be able to somehow withdraw this money later on with fees. Okay, so let's now try and write a transition that will allow to add some liquidity. Yeah. So we are adding liquidity by providing token 1 and token 2. Okay. Oops. Yeah, and we will return. What do we need to return? Probably nothing, right? As we are adding liquidity, and so we are adding the whole amount for simplicity. So there will be no change in this case. Okay, and so this transition will also have finalize part, as we need to change program state to so that it has information about this liquidity addition. Okay, so here we just need amounts. We need amounts, and we need okay, and we need owner, address of the owner, token 1, token 2. Okay, so here we will modify the mappings. Okay, so let's see how we can work with mappings. Okay, so we'll get our reserves. Okay, for both tokens. Okay, it's reserves 1 U8, and so it will be reserve 1. Okay, and the same code will yeah, I think it will be probably safer to use get or use, which allows us to supply the oh, it's not you, sorry, yeah, 0, which allows us to specify the default value. So if there is no value for in reserves mapping, so there is no value for key 1 or 2 respectively. Okay, and yeah, so we got, and also let's get total supply y2, which is equal to, okay, so to mapping get total supply 0. So again, we have to use the whole mapping to store a single value, like not very convenient to be honest, but yeah, we have what we have. Okay, so now we have like we are adding liquidity, so there is token 1. Okay, so let's add a call to finalize, then finalize. Okay, yeah, so let's provide self caller, which is a special like a special value that stores the address of a user which called this transition. I mean, like the account, to be more precise. Okay, and token 1 amount and token 2 amount. Okay, so we are once yeah, just to elaborate a little. So we passed these 2 tokens into this transition, and it means that these 2 records are consumed. So they do not exist anymore. They exist, but they are marked as used. It means that user won't be able to use this token and this token, again, these records are spent, and yeah, they are spent, and now we are writing the finalized part that is executed on chain. So again, to remind you, the transition, this part is executed locally, and a ZK proof is generated for this execution. And this part is executed on chain, and it has access to the mappings. Okay, so let's now calculate LP1 as it's token 1 multiplied total and divided by reserve 1. Yeah, I hope it is correct. Yeah, okay, so we'll, yeah. I just realized that actually using 0 was not necessary, as like this. This part will fail anyway, as it will be division by 0. Okay, so LP1 and LP2. So we are dividing by reserve 2. And again, so everything, all the arithmetical operations are controlled, so they're over, what's the word? Okay, I lost the word. Yeah, so it cannot like overfill your uint, and you won't get some weird value. Okay, and the actual LP will be LP the minimal value. Okay, I think I will copy a minimal function from, yeah, to write it from scratch. Yeah, so essentially it calculates minimal value between A and B, just selects which is smaller, just a useful utility. Okay, so, and the actual LP, this is just like the way the math of AMM works. I mean, if you don't understand, well, no worries, it's something pretty specific. Yeah, so we're choosing the smaller one, and then we are updating the mapping. So reserves are topped up. So it's 1 EU and reserve 0 plus token 1. Oh, reserve 1. Yeah, sorry. Reserve 1. And here 2U8 reserve 2 plus token 2. So we are updating the state of the pools, and yeah, now we are supposed to update also the total supply. Yeah, so we're taking total supply and 0U8 and total plus LP. Okay, and so this is a total supply. So we updated reserves, we updated token supply. Yeah, and now we have to update user balance. So I'll let current balance which is equal, yeah, LP, how do I call it? LP balances. LP, okay, mapping get LP balances. Oh, okay, so yeah, actually I made a small mistake here. We don't want to use address in this mapping, as it will mean that everyone will be able to see who deposited how much, which is not what we want in private chain like Aleo, but we have to still take care of it ourselves. Okay, so let's replace this call with call to PHP 256 hash to field. It is a hash function, well, so it kind of hides the address of the caller, and well, anyone who has access to the mappings, and well, any person with access to Explorer has access to mapping of any program. And yeah, so we made our exchange truly private. Okay, so, and we are getting yeah, so owner and yeah, get or use again. So if the person deposits first time, there will be no record with his name, with his like hash in LP balances mapping, and well, it means we have to take care of it. Yeah. So this is the current balance of the user, and yeah, we are updating it with LP he provided. Okay, so mapping set LP balances owner and current balance plus LP. Okay, so what we have now, yeah, let's double check what we have already. So we have we are building an AMM, and we have 2 tokens. We can mint them, we can transfer them, and we can add liquidity to our pool. And so we are storing the reserves for token 1 and token 2. So we are updating them, and we are also storing LP token, which represents kind of the total amount for the user, like how much money he provided into this program. Okay, so yeah, let's now move to, yeah, I think we'll probably skip removing liquidity and go to swapping. Okay, so again, we are creating a transition, swap to 1. Yeah, so we are swapping to token 1. So what are we supposed to provide? We are supposed to provide token 2, and well, let's say the receiver will be the same. Okay, so we want to specify the amount in and an amount out. So how much we want to receive. So here is the tricky part. So if you ever use something like Uniswap, well, of course, you are not the one who like specifies the amount out, as it is calculated inside the contract. Here in Aleo, it's not that easy if we want to remain private. As well, in transitions and like this part of transition that is executed off-chain, we don't have access to mappings, as this program is run on our machine, so we don't have access to the chain state. So we are expecting front end to provide us certain amount. So this front end would read the state of mappings and calculate the appropriate value of amount to be received by a user. Okay, and yeah, so what we need to return is a change. Yeah, so we need to return token 2, as this amount can be lower than the whole record. So if you have a record of that contains 100 of tokens, but you want to exchange only 50, you can provide this token, this record, and specify the amount in. Okay, so what are we doing here? So here we just so user wants token 1. The owner will be the caller of this transition, and the amount is amount out. Okay, so what is complaining about? Token 2. Oh no, yeah, I was wrong. Yeah, actually, of course, I need to return 2 tokens. Yeah, so let's extract a variable for clarity then. So this one is exchanged, and token 1, and the other is change token 2. Token 2, owner, again caller, and amount is token amount, so the amount from the record provided by a user, and minus amount token 2. Yeah. So yeah, the amount to be exchanged. So in here again, it is automatically checked that token 2 amount is larger than amount in, larger or equal. Okay, so let's then we return exchanged and change, and then finalize. So inside finalize block, we will do inside finalize we will do an actual check that the exchange rate requested by user can actually be met, kind of by our pool state. Okay, so again here, what data we need here? Here we need the amounts, and let me think. We need only amounts. Yeah, we need amount in and amount out. Okay, so we are calling it with amount in and amount out. So what we need to do here, so we need to get the state of our reserves. So I will copy this code and show it. Okay, now we should update new reserve 1 is reserve 1. So we are swapping to 1. It means that we are subtracting amount out from new reserve, from the old reserve, and we are adding to the second token amount in. Okay, and now we'll need to okay, so here we'll add a check. It's like our to-do, not to forget about it. Yeah, and here we update the state of our program. So reserves are updated. Set reserves 1 with new reserve 1, and the same for reserve for the second token, essentially. Okay, so now we have the only thing to check is constant product condition that should remain the same after this swap. Okay, so we multiply new reserve 1 to new reserve 2, and this value should be more or equal when compared to reserve 1 multiplied to reserve 2. Yeah, so this is essentially the main line, I mean, that makes sure that our AMM actually exchanges according to the rules of the simple AMM, which yeah. Okay, so we can repeat the same code for token 2. So we essentially need to change everywhere token 1 to token 2, and token 2 to token 1. Yeah, it's not very difficult. And here swap to 2. Okay, swap to 2, and yeah, so reserves calculated the same. New reserve, so we are changing this line. Oops, yeah, so we are adding to token 1 reserves and subtracting from reserve 2. Okay, so we updated, yeah, this line remains the same, and this line remains the same too. Okay, so we implemented adding liquidity, swapping, and well, I think we still have some time to implement removing liquidity too. Okay, so remove liquidity. What we need to provide. Okay, so again, we assume that the receiver will be the same as caller. We are returning token 1 and token 2. Yeah, probably we want to specify the amount of the amount to be removed. Okay, and probably, yeah, we want this amount for both tokens. So we have amount, okay, let's call token 1 amount, let's call it amount for clarity, and token 2 amount. And yeah, now, well, we can add some checks. I think, yeah, we can, for example, check that token 1 amount is more than 0, for example. Yeah, and token 2 amount is also more than 0. Yeah, there are several types of assert. So there are assert that just accepts any Boolean expression, and there are some others like assert equality of 2 values or non-equality of 2 values, which is a pretty useful thing to have for a programming language. Okay, so let's return. Let's token 1 is a token 1 where owner will be self caller, and amount will be the exact amount requested by user. So again, we are using the same pattern. So in the first part of transition, which is executed on local machine, we are just accepting values from user and create records as if all the values provided are correct. And then on the finalize part, which is executed on chain, we check that actually the values are indeed correct. Okay, as well, user might not provide any liquidity, but they request like some amount of token 1 and token 2. And well, this transaction, and he can actually run this transition on his machine and generate ZK proof that like the calculation was correct, but his transaction won't be finalized because on-chain part will fail. So this is, I mean, this is an important thing to note when developing on Aleo. This is a very popular pattern, I'd say. Okay, so what we are returning, yeah, token 1 and token 2, and then finalize. Okay, so again, transition, finalize, yeah, finalize, remove liquidity, and yeah, token 1 amount, token 2 amount, and we also need an owner, which will again be a hashed PHP 256 hash to field self caller. So again, we do not expose the address of the caller of this function for any external observer. Okay, and here we pass token 1 amount and token 2 amount. Okay. Okay, so what we need to check inside the finalize block, we need to, again, we'll probably need these values. Yeah, unfortunately, currently you cannot extract functions from your transitions that can access mapping. So you can have like stateless utility functions like this one, but you cannot extract something like this part of code as it accesses a state, program state. Okay, yeah, so we have reserves, and we'll need to update reserves. Okay, so minus reserve 1 minus token 1 amount, and reserve 2 minus token 2 amount. Okay, and we'll also need to update total supply with some value. We need to figure out how to calculate that correctly. Okay, we also need to get user balance. Yeah, so here is the code that can do this. So current user balance, and yeah. Okay, let me double check that I'm doing it right. Okay. Yeah, so we need to, yeah, we got the balance, and now we need to figure out whether user has enough liquidity, or yeah. So let's see how to do this correctly. Yeah, we need to assert that token 1 amount is less than or equal token 2 amount. So we are dividing token supply, so we need total supply, right? And where do we store it? Yeah, total supply. So we are calculating yeah, so how much user current balance. Okay, so its current balance is his LP, and we divide current balance to total and multiply it by reserve 1. So yes, let me double check. Yeah, I hope this is correct. Yeah, should be correct. Current balance divided by total multiplied by reserve 2. Okay, yeah. So here essentially we are using current balance, and well, these two lines allow us to make sure that user is trying to withdraw some tokens that he actually has. He has enough LP tokens to cover this withdrawal. Okay, yeah, now it is correct. And we should also, yeah, total supply will be total minus token, yeah, minus users current balance. Yeah, so user is expected to withdraw the whole amount. So it's 8. Yeah, I hope Leo will add like simple variables to top level programs so that we don't have to use mappings for what shouldn't be a mapping actually. Okay, and here yeah, so we updated reserves and we updated total supply, and now, yeah, user, we are removing user LP tokens so that he cannot withdraw again. Owner, it's not receiver, it's an owner here. Okay, so yeah, it took us like 50 minutes to code a simple AMM swap, which is private. So it uses the power of Aleo to its max when it comes to like solving a simple task of swapping two tokens. So we can add liquidity, or we can remove liquidity, and we can do swaps. We can swap token 1 to token 2 and token 2 to token 1. And I think in the next lecture we'll see how to deploy this program, how to run it, and like how to interact with Aleo and use tooling. That's it for today. So thank you everyone for coming, and see you on the next